Welcome to this explainer. Imagine for a second that you're staring at a screen, searching for a tiny shadow that could literally mean the difference between life and death. Capturing a clear medical image to find things like tumors isn't just about snapping a quick, good-looking picture. It's an incredibly complex, high-stakes scientific process. So today, we're going to unpack the massive balancing act happening behind the scenes every single time a patient steps into an imaging machine. Okay, let's dive into this. When we talk about image quality in a medical context, we aren't talking about aesthetics. We don't care if the picture's pretty. Quality here is defined entirely by clinical utility. It's the degree to which an image actually allows medical professionals to accomplish their goals, whether that's accurately diagnosing a fractured bone from an X-ray or mapping out a highly precise millimeter-perfect radiotherapy plan for a cancer patient. In this world, quality equals usefulness. To make sense of it all, we've organized this hugely complex system into 5 quick chapters for today's explainer. First, the stakes of image quality. Second, contrast and resolution. Third, noise, artifacts, and distortion. Fourth, the ultimate goal of accuracy. And finally, the human-machine imaging system. Chapter 1. The stakes of image quality. What exactly are we measuring here? Before we can even talk about improving a medical image, we have to establish what we're actually managing when we look inside the human body. Image quality is not just some magic enhance button you press on a keyboard. It's a delicate composite of at least 6 distinct, heavily interrelated factors. We're looking at contrast, resolution, noise, artifacts, distortion, and accuracy. An imaging system, and the human operator running it, has to constantly juggle these 6 variables because tweaking one almost always messes with the others. Mastering this balance is the absolute key to a proper diagnosis. Moving right along to Chapter 2, Contrast and Resolution. Seeing the details. Contrast and resolution are the heavy hitters that fundamentally dictate our ability to clearly see an object. Think of medical imaging as a giant translation game. Tissues have different physical properties inside the body, right? Things like their density or their atomic number, which physicists call Z. The imaging process takes those physical differences and translates them into distinct visual shades of gray or color. High contrast means there's a huge glaring difference in those grayscale values, so features pop right out at you. Low contrast, the difference is minute, rendering those anatomical parts incredibly difficult to spot. You're basically flying blind. Now, what's really interesting about this slide is that contrast mathematically boils down to just the number 2. At its core, contrast is literally just the mathematical difference between 2 specific pixel intensity values. For example, comparing the pixels of a tumor directly against the pixels of the healthy tissue right next to it. But contrast is only half the battle. We also need fine detail, which brings us to resolution. Body structures vary wildly in size, from massive organs and thigh bones all the way down to tiny trabecular patterns in the bone and microcalcifications in tissue. And we are very often hunting for those minuscule, potentially life-threatening details. If an image lacks resolution, it lacks that fine detail. And the primary culprit behind poor resolution? Image blur. This brings us to a fundamental, unbreakable rule of medical imaging. The smallest object or detail that can be imaged has approximately the same dimensions as those of the image blur. Basically, image blur physically caps your resolution. It ruins your contrast and your detail all at once. If your blur dimensions are larger than the tiny microcalcification you're desperately trying to find, the blur is just going to swallow it up entirely. You won't even know it's there. Chapter 3, Noise, Artifacts, and Distortion, or as I like to think of them, the villains of imaging. If contrast and resolution are the heroes trying to reveal the body's hidden secrets, these next 3 factors are absolutely the villains. These are the technical interferences that obscure the truth or worse, outright lie to the medical observer. There are 3 main visual interferences here. Think of image model or noise, like static on an old radio, just completely drowning out the song. Artifacts are like hearing a phantom voice on that radio that isn't actually broadcasting at all. And distortion is an altered reality, like trying to examine a patient through a funhouse mirror. Let's break these down. First up is image noise, also known as image model. This is what gives an image that awful, textured, grainy appearance. It is a massive problem because it actively masks the features you need to see. Now, where this noise comes from and how bad it gets depends entirely on the imaging method you're using. For instance, nuclear medicine, that technique naturally yields images with some of the absolute highest noise levels in the field. Next up, artifacts. This happens when the machine creates features on the screen that do not represent a real body structure. Imagine scanning a patient's head and seeing a strange, pronounced shape right in the cranium, only to realize there is absolutely nothing there in real life. It's a glitch. Artifacts can cover up real anatomy, or horribly, they can be misinterpreted as actual medical issues, leading to some incredibly dangerous medical decisions. The third villain is distortion. A medical image can't just make internal organs visible. It absolutely must give a perfectly accurate impression of their size, their shape, and exactly where they are relative to everything else. Distortion provides a false impression of the anatomy. If a surgeon is relying on a scan to plan a delicate operation, they need the precise, true reality of the body, not a stretched or warped version of it.
All of these potential technical flaws force the radiologist to ask one overriding essential question when they look at any scan. Does this image tell the clinical truth?
Which leads us perfectly into Chapter 4, the ultimate goal: accuracy.
So the crucial point is, if you don't have accuracy, every single other factor we just talked about is completely meaningless. Accuracy is defined as both the conformity to truth and the clinical utility of the image. Remember, we judge quality purely on utility for a specific job. Remember how we just said nuclear medicine is super noisy? Well, if that specific, noisy nuclear technique is the absolute best way to detect a certain type of tumor, it wins. We prefer it. It is the most accurate choice for that specific clinical application because its utility is superior despite the static.
Finally, Chapter 5, the human-machine imaging system, putting it all together in the real world. We've thrown a lot of physics concepts around, so let's pull the camera back and look at how this interconnected system, as described by medical physicist Perry Sprouls, actually works in a clinic. It starts with Step 1, the input signal. That's the patient or the tumor we're hunting for. Step 2 is the imaging system. But this machine isn't on autopilot. A human operator actively manipulates it, dialing in crucial parameters like tube voltage or current. The operator's choices directly dictate Step 3, the final image quality, balancing all the contrast and noise, which finally hands the baton to Step 4, observer detection.
Detecting a pathology isn't just about handing over a good image. It's actually a combination of three distinct things. Yes, the image quality is vital, but whether a doctor finds the tumor also relies heavily on the viewing conditions in the room, like the lighting and monitor quality, and crucially, the observer's own performance. The human element at the very end of this chain is just as critical as the high-tech machine at the beginning.
Which leaves us with this final provocative thought to chew on. If an imaging machine perfectly captures a tumor with pristine contrast and flawless resolution, but the human viewing conditions in the diagnosis room cause the observer to miss it entirely, was the medical imaging process truly a success? It really highlights that medical imaging is never just about taking a high-tech picture. It is an inseparable, high-stakes partnership between machine precision and human interpretation. Thanks for joining me on this explainer, and keep questioning what you see.